Good morning, good afternoon, and good evening to everyone who joins us from around the world.
We're so glad you're here.
This is Andrew and Renee.
Welcome to the Stack series,
Today, we are exploring physics beyond the standard model.
which is, I think, without any exaggeration, probably one of the most ambitious topics we've ever decided to tackle.
It really is. I was sitting with this huge stack of research you sent over yesterday. I had my coffee, my highlighter out, feeling pretty confident. Thought, okay, physics, I get this. Gravity, atoms, electrons, I'm with you.
And then you actually open the files.
And then I started reading. And I got this really distinct feeling. It wasn't confusion, not exactly. It was more like vertigo.
Vertigo. I like that.
Yeah, it's that feeling you get when you've just finished a really hard puzzle, 1,000 pieces, a whole landscape.
Yeah.
You put that last piece in, you step back, and you feel that satisfaction. But then you suddenly realize the puzzle is sitting on a small table in the middle of a colossal pitch-black room. And you have absolutely no idea what else is in that room with you. The puzzle is perfect, but it's not the whole picture.
That is a surprisingly perfect analogy for where we are in high-energy physics right now.
Really?
Absolutely. We are staring at what is, without a doubt, the most successful scientific theory in human history, the Standard Model.
Yeah.
And we are at the exact same moment realizing it cannot possibly be the final answer.
It's those glaring holes in the map that really get me. We're not just talking about, tweaking a number in the fifth decimal place.
No, not at all.
We're talking about the fundamental ingredients of reality. Things like what most of the universe is actually made of. We know it's out there, but our current instruction manual, the Standard Model, doesn't even mention it.
Exactly. I mean, the Standard Model of particle physics, it's a triumph. It predicted particles like the Higgs boson decades, literally decades, before we built a machine powerful enough to find it.
It's incredible.
It explains electromagnetism, the weak nuclear force, the strong nuclear force. It's been battle-tested for 50 years.
Yeah.
But like you said, it's fundamentally incomplete.
So that's what we're going to do today. That's our mission. We're going to explore those cracks in the puzzle. We're going to look at the anomalies that are keeping physicists up at night, the big missing pieces like dark matter and the absolutely mind-boggling machines they're designing to find them.
Yeah, these future colliders are something else. So we've got a lot of ground to cover. We should probably start with the foundations, what we think we know.
Right.
Then we'll get into the active debates, which is, where science is really fighting with itself right now.
Yeah.
That's the juicy stuff.
Okay.
After that, the frontiers of detection. And finally, we have to ask, what does all this cost? And why on earth should anyone care?
Okay, let's do it. Let's start with the foundation, the Standard Model.
Right.
I often hear it described as a kind of periodic table for particle physics. Is that a fair way to think about it?
It is. It's a great starting point. But in some ways, it's even simpler than the chemical periodic table. If you zoom in on the universe down to the smallest possible scales, you find it's all made of a surprisingly small number of ingredients.
Okay.
You've got your fermions. These are your matter particles.
The fermions, so these are the actual stuff, the bricks of the house.
They're the bricks, exactly. You have quarks, which clump together to make protons and neutrons. That's the nucleus of every atom.
Right.
And then you have leptons. The most famous lepton, of course, is the electron, which orbits that nucleus. Everything you can see, touch, or stub your toe on is made of these fermions.
But a pile of bricks isn't a house. You need something to hold them together. You need cement.
Precisely. And in the world of particle physics, the cement is the bosons.
The boson.
These are the force-carrying particles. They're like little messengers that communicate the fundamental forces of nature between the matter particles, between the fermions.
Okay, so give me the roll call of these force carriers.
So first you have the photon. You're familiar with this one, even if you don't know it. It carries the electromagnetic force.
So that's light, electricity.
Light, electricity, magnets sticking to your fridge, radio waves, all of that. That's the photon doing its job.
Got it.
Then you have gluons. They carry the strong nuclear force. And the name is perfect. They literally glue quarks together inside protons and neutrons. It's the strongest force in nature, but it only works over tiny, tiny distances.
Okay. And the last one?
The W&Z bosons. These carry the weak nuclear force.
The weak force. It always sounds like the underdog, the least important one of the group.
It sounds wimpy, I know, but it's absolutely essential. The weak force governs radioactive decay. More importantly, it's crucial for the nuclear fusion processes that power the sun.
So without the weak force?
The sun wouldn't shine. Life wouldn't exist. We wouldn't be here having this conversation. So, not so wimpy after all.
Right. And the absolute crown jewel of this entire collection, the one they spent decades looking for, was the Higgs boson. I remember the media storm in 2012 when they finally found it at the LHC.
The keystone. Yes, the discovery at the Large Hadron Collider at CERN it was monumental.
So the standard model predicted that for other particles to have mass, there had to be this invisible field everywhere in the universe, the Higgs field.
That's right.
Okay, can we pause on that for a second? Because mass feels so fundamental. It just is. Why do we need a whole field to explain why something has weight?
It's a great question because it is a very counterintuitive idea.
Yeah.
Think of it like this. Imagine you're in a room and the entire room is filled with, say, very thick, heady snow. That's the Higgs field. It's just there everywhere.
Okay, a room full of snow.
Now imagine a skier trying to cross that room. They've got skis on. They just glide right over the top of the snow, moving really fast. They interact very little with the snow field.
So that's like...
It's like a photon.
Yeah?
It has no mass. It zips along at the speed of light, barely noticing the Higgs field is there.
Okay, makes sense.
Now imagine a second person, but they're just wearing big, clunky snow boots. They try to walk through that same deep snow.
They're going to get bogged down.
Totally bogged down. They move much slower. They're constantly interacting with the snow, pushing it out of the way. They have, in effect, acquired mass from their interaction with the field.
So that's like an electron or quark.
Exactly. The more a particle interacts with the Higgs field, the more massive it is.
So then what is the Higgs boson itself, the particle they found?
The Higgs boson is what happens if you were to walk into that room and slap the snow. A little puff of snow, a little clump would fly up into the air.
Ah, so it's an excitation of the field.
It is the excitation of the field itself. It's the proof that the snow is really there. Finding that puff of snow in 2012 at CERN was the final, stunning verification of the Standard Model's core structure. It all worked.
So, okay, 2012, champagne corks are popping, Peter Higgs is crying tears of joy, the model is complete. But the hangover from that party seems to have set in pretty quickly.
It did.
Because for all its incredible success, the Standard Model is, well, it's completely ghosting gravity.
Completely silent on it, yes. This is the first and maybe the most obvious crack in the whole foundation. On the one hand, we have general relativity, which is Einstein's masterpiece.
Right.
It describes gravity as this beautiful geometric thing, the curvature of space-time. Think of a bowling ball on a rubber sheet. It's smooth, it's continuous.
Geometric, predictable, I get it.
And then, on the other hand, you have the Standard Model. It describes the quantum world. And that world is not smooth. It's pixelated, it's jittery, it's all about probabilities and discrete packets of energy.
And the two just don't get along.
They are mathematically, fundamentally incompatible. If you try to write down an equation that includes both the smooth math of relativity and the jittery math of quantum mechanics, the equation just breaks. You get nonsense answers. You get infinities all over the place.
So we have two perfect theories describing our world, but they seem to describe two different worlds that can't coexist in the same mathematical framework.
That's it. Which is deeply unsettling. The Standard Model works perfectly as long as you pretend gravity doesn't exist.
Right.
But, you know, we're both sitting in chairs right now, not floating away, so we know it does.
Okay, that's strike one. But you told me strike two is even bigger. It's about what the universe is actually made of.
Yeah, I love this statistic because it's so humbling. The Standard Model, this incredible theory, explains what percentage of the universe's mass and energy do you think it explains?
I mean, based on how you're setting this up, I'm guessing it's not 100%?
Maybe.
Half? 5%.
Try 5.
5%.
5%,
Yeah.
roughly. That's all the visible matter. It's the stars, the galaxies, the gas clouds, you, me, this table, the coffee you drank this morning. Everything made of atoms adds up to a measly 5% of the cosmic budget.
That's insane. So where's the other 95%?
Yeah, it's what we call the dark sector. About 27% of it is something called dark matter. This is some kind of invisible mass. We can't see it, but we can see its gravitational effects. It forms these giant halos around galaxies, and without its gravity holding them together, galaxies would spin so fast they'd just fly apart.
So it's the cosmic scaffolding.
A perfect way to put it. And the rest, the huge remaining 69%, is even weirder. It's dark energy.
Dark energy.
This is some kind of energy inherent in space itself that is causing the expansion of the universe to accelerate. It's pushing everything apart faster and faster.
And what does the Standard Model, our great instruction manual, have to say about these two things that make up 95% of reality?
Nothing. Not a word. It has no candidate particle for dark matter. It has no explanation at all for dark energy.
It's like buying a car manual that only explains how the glove box light works, but completely ignores the engine, the wheels, the transmission, and the chassis.
That is a perfect analogy.
Right.
And believe it or not, it gets worse.
How can it get worse?
Well, because we exist.
I feel like that's generally a good thing. Why is our own existence a problem for physics?
In the context of the Big Bang, it's a huge problem. See, the laws of physics, as described by the Standard Model, are, for the most part, very symmetric. This means that the Big Bang should have produced equal amounts of matter and antimatter.
And antimatter is like matter's evil twin, right?
Yeah.
Same mass, but opposite charge.
Exactly. An anti-electron has a positive charge. An antiproton has a negative charge. But here's the crucial part. When a particle of matter meets its antimatter twin,
They annihilate.
they annihilate. Poof. They turn into pure energy, a flash of light. So theoretically, the early universe should have been this massive, chaotic annihilation event. Everything should have canceled everything else out,
Leaving nothing.
leaving nothing but a bath of leftover radiation. No stars, no planets, no people. But you're here, I'm here, so clearly that's not what happened.
So somehow, a tiny bit of matter survived.
A tiny fraction survived. For every billion pairs of matter and antimatter that annihilated, maybe one matter particle was left over with no one to dance with. This is the matter-antimatter asymmetry, and the Standard Model, as it stands, simply cannot fully account for it. It can't explain why the scales were tipped in favor of matter.
Okay, so just to recap. Gravity is missing, 95% of the universe is missing, and the very fact that we exist at all is a huge mystery.
That about sums it up.
And then there are the neutrinos.
Ah, the neutrinos.
Ah,
The ghosts of the particle zoo. They always cause trouble.
why are they such a problem?
Because the Standard Model, in its original, most elegant form, predicted that they should be massless, just like photons.
And they barely interact with anything, right?
Barely is an understatement. There are trillions of neutrinos from the sun passing through your body every single second as we speak, and you don't feel a thing. They could fly through a light year of solid lead and not hit anything.
But we found out they're not massless after all.
Correct. We discovered a phenomenon called neutrino oscillation. See, neutrinos come in 3 different flavors. There's an electron neutrino, a muon neutrino, and a tau neutrino.
Okay.
And what we observed is that as they travel through space, they change. They morph from one flavor into another.
It's like ordering vanilla ice cream, and by the time it gets to your table, it's turned into chocolate.
It is exactly like that. And according to the fundamental laws of quantum mechanics, that flavor-changing act is only possible if the neutrinos have mass. It's a tiny mass, millions of times lighter than an electron, but it is not zero.
And the Standard Model had no place for that.
No mechanism to give them mass. It was a complete surprise, and we had to sort of tack it on after the fact. It's not an elegant part of the theory.
Okay, I want to unpack one last foundational issue before we move on, because I see this phrase all the time in the papers, the hierarchy problem.
Yes.
It sounds like a corporate management issue, but I get the sense it's about the Higgs boson being too light.
It is. It's also called the naturalness problem.
Yeah.
And this is the one that really, really keeps theoretical physicists up at night. It's a bit abstract, but here's the gist.
Lay it on me.
So we measured the Higgs boson's mass. It's about 125 gigaelectron volts, or GeV. That's roughly the mass of a large atom like iodine. Seems fine.
Okay, a reasonable number.
But according to quantum mechanics, the Higgs is not alone in the universe. It's constantly interacting with a sea of virtual particles that are blinking in and out of existence in the quantum foam.
Right.
These interactions, especially with the heaviest known particle, the top quark, should add huge corrections to the Higgs's own mass. They should drag it up.
How huge are we talking?
We're talking.
Yeah.
Theoretically, they should push the Higgs mass all the way up to the Planck scale. That's the energy scale where quantum gravity becomes important. It's about 10 to the power of 18 GeV.
10 to the
Okay.
18. So that's a 1 with 18 zeros after it.
Yes, that's 16 orders of magnitude heavier than what we actually observe.
Whoa. That is not a small discrepancy. That's like predicting a newborn baby will weigh 8 pounds and it comes out weighing as much as the entire planet Earth.
That is exactly the scale of the error. So the question becomes, why is it so light? How is this happening? It's like trying to balance a perfectly sharpened pencil on its tip
Okay.
on a table that is shaking violently during a massive earthquake. In theory, it's possible for the pencil to stay upright, but it would require an unbelievable, almost miraculous cancellation of all the shaking forces, an insane amount of fine-tuning.
And physicists hate fine-tuning.
They despise it. It feels like a cheat. They want a natural explanation. They want a physical reason why the pencil is stable.
And for a long, long time, the leading candidate for that physical reason was something called supersymmetry.
Yeah.
SUSY.
Yes. SUSY is, on paper, one of the most beautiful ideas in physics.
What's the core idea?
The idea is that the universe has a hidden symmetry. For every fermion or matter particles, there exists a boson superpartner. And for every boson or force particles, there's a fermion superpartner.
So the electron would have a partner called the selectron.
The pholectron. And the top quark has a partner called the stop squark.
Stop squark! I swear, physicists are just the worst at naming things. Selectron sounds like a brand of budget kitchen appliances.
The names are a bit whimsical, I'll grant you that. But the mathematics is breathtakingly elegant. Because these superpartners would solve the hierarchy problem perfectly.
Ow.
The quantum corrections from the regular top quark, which want to make the Higgs super heavy, would be mathematically canceled out by the corrections from the stop squark. A+ cancels in minus. The pencil on the table is suddenly stable because for every shake to the left, there's a perfectly equal and opposite shake to the right. The Higgs stays light, naturally.
It sounds perfect, but, and this is a very big, but we haven't found any of them.
We have not found a single one. The Large Hadron Collider was built in large part to be a SUSY discovery machine. We've been smashing protons together at incredible energies for over a decade, and we've seen absolutely no sign of squarks or leptons or any of these superpartners.
So what does that mean for the theory? Is it dead?
It's in a state of crisis. As one of the papers put it, no SUSY, no naturalness. If SUSY is real, its particles must be much, much heavier than we originally thought, which is why the LHC hasn't seen them.
But if they're too heavy,
then the cancellation isn't perfect anymore. We're back to needing some fine-tuning. We're pushing the theory into these awkward corners of parameter space just to hide it from our experiments, which kind of defeats the whole purpose of what made it so attractive in the first place.
So the easy fix, the one everyone was betting on for 30 years, is looking less and less likely.
That's right.
Which brings us perfectly to the second part of our conversation today, the active debate. Because while we haven't found this beautiful, clean solution, we have found some weirdness, some anomalies in the data.
Some very tantalizing weirdness.
And the biggest one, the one that seems to be the main drama in physics right now, is the muon G2 anomaly.
It really is. It's like a civil war is broken out between the experimentalists and the theorists. It's fascinating to watch.
Okay, first, remind us, what is a muon?
A muon is basically a heavy cousin of the electron. It has the same negative charge, but it's about 200 times more massive.
And because it's heavy?
It's more sensitive. It feels the effects of that quantum foam of virtual particles we talked about much more strongly than a light electron does. It's a better probe for new undiscovered physics.
And the experiment, it's at Fermilab near Chicago, and it basically involves making muons wobble.
That's a great way to put it. The muon G2 experiment shoots a beam of muons into a giant, perfectly circular magnetic ring. Now, when you put a spinning charged particle into a magnetic field, it doesn't just go in a circle. It also precesses. It wobbles, just like a spinning top does as it slows down.
And the standard model has a prediction for how fast it should wobble.
An incredibly precise prediction. The value is called G2, and the standard model predicts it to something like 12 decimal places. It's one of the most precise calculations in all of science. It accounts for the muon interacting with every known particle.
Okay, so the theory is rock solid. Fermilab measures the wobble. What happened?
They released their big results in 2021 and then confirmed them with even more data in 2023.
Yep.
And the result is the muon is wobbling too fast. It's precessing slightly more than the standard model says it should.
How big is the difference? I see this term sigma used a lot.
The difference was around 4.2 sigma. Now, in statistics, sigma is a measure of how unlikely a result is due to random chance.
Okay.
In particle physics, we have a very high bar. 5 sigma is the gold standard for claiming a discovery, so 4.2 sigma is huge. It means there's only about a 1 in 40,000 chance that this is just a statistical fluke.
So it's a really strong hint that something is wrong.
It's a smoking gun. It implies that there are unknown particles, things not in the standard model, that are also part of that quantum foam and are pushing on the muon, making it wobble just a little bit faster than it should.
That sounds amazing. We found new physics. Open the champagne.
Well, it looked that way. It really did. But, and this is the incredible twist in the story, the theoretical prediction itself is now under attack from other theorists.
Wait, so you're saying the experiment might be correct, but the number we're comparing it to, the standard model prediction, might have been calculated wrong.
That is exactly the heart of the debate. It turns out that calculating that G2 value is monstrously difficult. And there's one particular piece of it, a term called the hadronic vacuum polarization, that is the main source of uncertainty.
Okay, that's a mouthful.
It basically describes how the muon interacts with a messy cloud of quarks and gluons. And you can calculate this term in two different ways.
Okay, give me method one.
Method one is the traditional data-driven approach. It's very clever. Instead of trying to calculate the quark cloud from scratch, which is super hard, you use data from other older experiments, specifically experiments that smashed electrons and positrons together. You take that real-world data and plug it into your G2 calculation.
And that's the number that disagrees with the Fermilab experiment.
That is the number that has been used for years, and yes, it creates that 4.2 sigma discrepancy. But recently, a different experiment, the CMD3 experiment in Russia, remeasured that electron-positron data. And their new data, when you plug it in, it changes the prediction. It moves the theoretical value much closer to the experimental one measured at Fermilab. The discrepancy almost completely disappears.
So, no new physics, it was just a problem with old data. That's kind of a buzzkill.
It would be.
Yeah.
But that's not the end of the story. There's method two.
Okay, what's method two?
Method two is called lattice QCD. This is a brute force, pure simulation approach. Theorists use some of the world's biggest supercomputers to simulate the strong force on a four-dimensional grid of space-time points of lattice.
So no experimental data, just pure theory and computer power.
Exactly. They calculate it from first principles. And several big collaborations have been working on this for years.
Yeah.
And their results.
They agree with the old predict.
They do. They predict a value that creates a large discrepancy with the experiment. They are essentially saying, yes, the wobble is weird. New physics is likely.
So let me get this straight. The experiment says something is weird. One group of theorists, using method one, says, no, it's not. Our calculation was just off. And another group of theorists, using method two, says, no, our calculation is right, and it really is weird.
You've got it. It is a total conundrum. We are in this bizarre situation where we don't know if we've discovered a new fundamental particle or if we're just in the middle of a 5-year-long argument about how to do a very, very hard calculation. It's a messy, beautiful, perfect example of how science actually works in real time.
It's incredible. So while the muons are wobbling too fast in Illinois, I read that B-mesons are decaying weirdly over at CERN. What are the flavor anomalies?
Yes, this is another set of very persistent hints. This is coming out of the LHC experiment at CERN and also the Bell-Leslie experiment in Japan. They are precision factories for studying particles that contain a bottom quark. We call them B-mesons.
And there's a specific rule they're supposed to follow when they decay, right?
A very important one. It's called lepton flavor universality.
That sounds like an ice cream shop policy where all flavors cost the same.
That's not a bad analogy at all. The standard model says that the weak force, which governs these decays, should not care what flavor of lepton it produces.
So electron, muon, or tau? Vanilla, chocolate, or strawberry?
Exactly. The weak force is supposed to be flavor blind. So when a B-meson decays, it should produce electrons and muons at exactly the same rate. The only difference should come from the fact that a muon is heavier than an electron, which is an effect we can calculate perfectly.
Universal. Got it. But the experiments are seeing something different.
They are seeing hints of a difference. For years, there have been these tensions, specifically in decays where a bottom quark turns into a charm quark and produces a lepton. The measurements of these ratios, which we give names like RD and RD star, are consistently off from the standard model prediction.
So nature might actually have a preferred flavor. It's discriminating.
It appears it might be. The tension is around 3 to 4 sigma. Not quite a discovery, but it refuses to go away. And it has revitalized interest in very exotic, very cool hypothetical particle.
Which is?
The leptoquark.
Leptoquark. That sounds like a mythological beast. A chimera.
It's a chimera of a particle. In the standard model, you have two distinct families of matter. Leptons, like the electron, and quarks, which make up protons. They don't talk to each other directly.
Right.
A leptoquark would be a bridge between those two worlds. It would be a single particle that could decay into a quark and a lepton simultaneously. It could turn a quark into a lepton and vice versa.
That sounds like it breaks all the rules.
It breaks the standard model's rules, but it fits beautifully into bigger, more ambitious theories, specifically grand unified theories, or GUTs.
GUTs, the idea that all the forces were once a single superforce in the early universe.
Exactly. In certain GOT models, like one based on a symmetry group called SO10, leptoquarks just naturally appear in the equations. They're not some weird thing you have to add in. They're a required part of the structure.
And I was reading one of the more dense papers about this. It said that these leptoquarks don't just solve the B-meson anomalies, they also help with something called Yukawa unification.
Yes, this is what makes it so compelling. In the standard model, the masses of the fundamental particles look completely random. There's no pattern.
Hmm.
But in these GUTs, there's a hope that at very high energies, these masses unify.
Okay.
And it turns out that the specific kind of leptoquark you would need to explain the B-meson anomalies is also exactly the kind of particle that helps the masses of the bottom quark and the tau lepton unify at the GUT scale.
So it solves two completely different puzzles for the price of one new particle.
Potentially, yes. It's like you find a single key that mysteriously opens two different locks. It makes you think the key might be real. It suggests that these flavor anomalies aren't just a statistical fluke, but a deep hint about a larger, unified structure of matter.
It's like pulling on a loose thread and finding it's connected to a whole different part of the tapestry.
A perfect metaphor.
Okay, before we get to the frontiers of how we actually find these things, there's one more anomaly I have to ask about. The neutron. Something about its lifetime and whether it's squashed.
Ah, yes, the strong CP problem. This ties all the way back to that matter-antimatter imbalance we talked about at the beginning. We need to find new sources of what we call CP violation to explain why we're made of matter.
Right.
And one place to look for it is in the properties of the neutron. Physicists are searching for something called an electric dipole moment, or EDM, of the neutron.
Most people, myself included, probably picture a neutron as a perfect little round ball.
Exactly. And if it's perfectly spherical, its internal positive and negative charge distributions are perfectly centered. It have no EDM. But if it does have an EDM, it means the charge is slightly separated. It would be ever so slightly squashed or oval-shaped.
Like a tiny football. Why does its shape matter so much?
Because a non-zero EDM, that squash shape, would violate a fundamental symmetry of nature. It would mean the neutron looks different if you run the film of its interactions backwards in time. And that kind of time reversal violation is exactly what's needed to generate more matter than antimatter in the early universe.
So have we found the squashed neutron yet?
Not yet. But the experiments are breathtaking. They have placed limits on the size of this EDM that are almost unimaginably small. The current limit is less than 10 to the minus 26 electron centimeters.
I can't even begin to visualize a number that small.
Let me try to give you an analogy. Imagine you took a single neutron and blew it up to be the size of the entire planet Earth.
Okay, a neutron the size of the Earth.
The squash that these experiments are looking for, the deviation from a perfect sphere, the little bump on the surface, would be smaller than the width of a single virus.
That is completely insane. And it brings us perfectly to the next section, the frontiers. Because to look for something smaller than a virus on an Earth-sized particle, you need some truly science fiction level detectors.
You really do.
Let's start with the LZ experiment. This is the big hunt for dark matter.
The LUXC Plin experiment, yes. This is our best shot right now at directly detecting this stuff.
I want to paint a picture here, because you sent me some photos of this thing, and it looks like a villain's lair from a James Bond movie. It's a mile underground in an old gold mine in South Dakota.
It is. The Sanford Underground Research Facility. You have to get in a literal mine cage and take an elevator down into the earth for about 10 minutes to get to the lab.
Why? Why go to all that trouble to bury $1 billion experiment under a mile of solid rock?
You're looking for silence. Absolute perfect radio-quiet silence. The surface of our planet is constantly being peppered by high-energy particles from space called cosmic rays.
Right.
This creates a huge amount of background noise.
Yeah.
If you're looking for an incredibly rare, incredibly faint signal like a dark matter particle bumping into one of your atoms, you have to get away from that cosmic chatter. The mile of rock above the lab acts as a massive shield.
And the detector itself, it's a giant tank filled with liquid xenon.
10 tons of ultra-pure liquid xenon. The theory goes that billions of dark matter particles, specifically a type called WIMPs, or weakly interacting massive particles, are streaming through the Earth all the time.
Okay.
The hope is that one of them, just one, might fly through the rock into the detector and score a direct hit on the nucleus of a xenon atom.
And if it does, what happens?
That tiny collision would cause the xenon nucleus to recoil, and it would release a tiny flash of light and knock a few electrons loose. The whole tank is lined with extremely sensitive light sensors that are waiting to see that one faint double flash of light.
But here's where the story gets a really fascinating twist. They released their latest results, and while they haven't found dark matter yet, they have definitively found something else: the neutrino fog.
This is a monumental turning point in the history of this kind of research. The LZ detector is now so astoundingly sensitive it has become the world's best detector for something it was even primarily designed to find: neutrinos from the sun.
Wait a second, I thought neutrinos were the ghost particles. I thought they were almost impossible to detect.
They are, but LZ is so big, so pure, and so quiet that it's now clearly seeing solar neutrinos, specifically high-energy ones from boron-8 decay, in the sun via a process called coherent elastic neutrino nucleus scattering.
Let me guess. The signal from a neutrino hitting a xenon atom looks a lot like the signal from a dark matter particle hitting a xenon atom.
It looks almost exactly the same. We have reached a point where our detector is so sensitive that its main source of background noise is no longer cosmic rays or radioactivity in the lab walls. It's an irreducible background of neutrinos coming from the core of our own sun. We call it the neutrino fog.
That feels so ironic, almost poetic.
Mm-hmm.
You build the quietest place on Earth to listen for a whisper from the cosmos, and the sun is still shouting in your ear. So what's the plan? How do you get past that?
You can't. You can't shield against neutrinos, so you have to build an even bigger detector. The plan is already in motion for a next-generation experiment called XLZD. If you have a much larger tank, you get much more data. And with enough statistics, you might be able to tell the difference between a neutrino-induced signal and a WIMP-induced signal by looking at subtle differences in their energy spectrum. You have to see through the fog by having a bigger telescope.
And speaking of neutrinos, they're not just a background noise. They're a whole frontier of their own. We mentioned DD earlier, the Deep Underground Neutrino Experiment.
Yes, DD is the flagship U.S.-based particle physics project for the next generation. It is massive in scale.
They're going to shoot a beam of neutrinos from Fermilab near Chicago.
The most intense neutrino beam ever created.
Straight through the Earth's crust. No tunnel, just through solid rock for 1,300 kilometers to a massive detector in the same underground mine in South Dakota where LZ is.
That's the plan. The primary goal is to study those neutrino oscillations, the flavor changing, with unprecedented precision. They want to see if neutrinos and antineutrinos oscillate differently, which would be another source of that CP violation we need.
But they're also trying to answer an even more fundamental question about the nature of the neutrino itself.
Yes, the big one. Are neutrinos their own antiparticles?
Okay, explain that. How can something be its own antiparticle? I thought matter and antimatter annihilated each other.
It's possible for a truly neutral particle. We call this a Majorana particle, as opposed to a Dirac particle like the electron, which has a distinct antiparticle. And if neutrinos are Majorana particles, it would solve one of their biggest mysteries. Why is their mass so incredibly tiny?
Okay.
It allows for a beautiful theoretical idea called the seesaw mechanism.
I love that name.
It's very descriptive.
Yeah.
Imagine a playground seesaw. On one end, you put a new, undiscovered, incredibly heavy particle, maybe a heavy right-handed neutrino that exists at the grand unification scale.
So a really, really heavy particle.
Because it's so heavy, it pushes its side of the seesaw way down to the ground. And what does that do to the other side?
It sends it flying way up in the air.
Exactly. And on that other side of the seesaw is our familiar light neutrino. Its mass is tiny because its partner's mass is enormous. The seesaw mechanism naturally explains the vast difference in scales.
And how on earth do you prove something like that?
By searching for an extremely rare type of radioactive decay. It's called neutrinoless double beta decay.
That's a mouthful.
It is. In normal double beta decay, a nucleus spits out 2 electrons and 2 antineutrinos. But if the neutrino is its own antiparticle, if it's a Majorana particle, then something amazing can happen inside the nucleus.
What?
The 2 antineutrinos that are emitted could find each other and annihilate each other before they ever leave the nucleus.
So you'd see the 2 electrons fly out, but no neutrinos.
Exactly. You'd see the decay, but with missing energy. If we ever observe this process, it's a guaranteed Nobel Prize. It would prove that neutrinos are Majorana particles, it would violate a sacred conservation law, and it would give massive support to these GUT theories and the seesaw mechanism.
It's incredible. Okay, finally, let's talk about the big guns. The machines of tomorrow, the colliders. The LHC is getting an upgrade, but everyone's eyes are on the FCC.
The Future Circular Collider. This is CERN's bold vision for what comes after the LHC, for the latter half of the 21st century.
The scale is just, it's hard to wrap your head around. The current LHC is a 27-kilometer ring The FCC would be a 100-kilometer ring.
It would encircle the entire city of Geneva and its surrounding countryside. The tunnel would have to pass under Lake Geneva on one side and under the Selev Mountain on the other. It is a mega project on the scale of the pyramids.
And I read it's a two-stage plan. It's not just one machine.
Exactly. And this is a very clever way to maximize the science. Stage 1 is FCC-EE, an electron-positron collider.
Okay, so not smashing protons?
No. Electrons and their antiparticles, positrons, are fundamental particles.
All right.
They're not messy bags of quarks and gluons like protons are. So when they collide, the results are incredibly clean and precise.
And the goal there is
To be a Higgs factory. It would produce millions upon millions of Higgs bosons and other particles and allow us to study their properties with a precision the LHC can only dream of. We want to see if the Higgs behaves exactly as the standard model predicts, or if there are tiny deviations that hint at new physics.
And after that's done,
Then, maybe in the 2070s or 2080s, you rip out all the electron-positron hardware from the 100-kilometer tunnel and you install the next generation of powerful superconducting magnets. And you build FCCHH.
a proton collider, like the LHC, but much bigger.
Much, much bigger. It would reach collision energies of 100 teraelectron volts, or TeV. That's 7 times the energy of the current LHC.
Why do we need that much more power? We already found the Higgs. What are we looking for?
We're looking for the heavy stuff directly. If those supersymmetric particles exist but are just too heavy for the LHC to produce, the FCCH could create them. If dark matter has a heavy particle associated with it, the FCC could make it in the lab. If leptoquarks are real, this is the machine that could discover them. Remember Einstein's equation, EMC2?
Energy equals mass.
To create heavy new particles, new mass, you need a huge amount of energy. The LHC is a powerful hammer, but the FCCHH is a sledgehammer designed to crack the standard model wide open and let us see what's really inside.
But this all leads us inevitably to the final crucial part of this whole story, the implications. Because digging a 100-kilometer tunnel under the Alps and filling it with futuristic magnets, that's not cheap.
It is not. The first stage, FCCE, has a price tag of around 15 billion Swiss francs. The full two-stage program would be significantly more.
That's a staggering amount of money. And people will rightly ask, why should we spend billions smashing particles when we have climate change, disease, poverty? What is the honest answer to that very fair question?
It is an extremely fair question, and it's one the scientific community has to answer. But if you look at the hard economics of these past projects, the return on investment, the ROI, is actually hugely positive. One study estimated it at about 1.8 times the initial cost.
How is that possible? Is CERN selling tickets to the tunnel tour?
No, it's about the technological spin-offs. You don't build a machine like the FCC by going to the hardware store. You have to invent things that don't exist yet. New types of superconducting magnets, new ultra-high vacuum technologies, new ways to process and store petabytes of data every second.
And these new technologies then find their way into the wider world.
They always do. The most famous example, of course, is the World Wide Web.
Invented at CERN.
Invented at CERN by Tim Berners-Lee simply because he needed a better way for thousands of physicists around the world to share their data. He wasn't trying to invent social media. He was trying to solve a physics problem.
But it goes way beyond the web, right?
Oh, massively. Medical imaging is a huge one. The technology behind MRI machines relies on the same kind of powerful superconducting magnets that were developed and perfected for particle accelerators.
And what about cancer therapy?
Hadron therapy. Using beams of protons or other particles to precisely target and destroy tumors while minimizing damage to surrounding tissue. That technology comes directly from the accelerator physics labs that built machines like the LHC.
So the argument is that fundamental research is a driver of innovation that pays dividends in completely unexpected areas.
That's a huge part of it. And the other part is the human capital. These projects train thousands of young scientists, engineers, and technicians. They learn how to solve problems that no one has ever solved before. They handle the biggest data sets in the world. Then they finish their PhDs, and many of them go out into industry, into finance, into green energy, into tech. They become the elite problem solvers for the rest of society.
There's also a deeper, more philosophical angle to all this, isn't there? I read about this debate between physicists facing a desert versus exploring a jungle.
This is the great existential question of modern particle physics. It's what keeps people awake at 3 a.m.
Okay, explain the desert hypothesis.
The desert is the pessimistic view. The desert hypothesis says that the standard model is basically correct, and that's it. We found the Higgs boson, and there's simply nothing else. No new particles, no new forces, no surprises, all the way up to the mind-bogglingly high Planck scale, where quantum gravity finally takes over. Just a vast, empty, energetic desert.
So if we build the FCC for tens of billions of dollars and find nothing.
Then we would have confirmed the desert, and that would be a valid scientific result, knowing there's nothing, there's still knowledge. But emotionally, for the field, it would be devastating. It would suggest that nature is done giving us clues at energies we can reach.
But you're more of a jungle person.
I have to be. The jungle hypothesis is the optimistic view. It says the universe is actually teeming with new physics. We just haven't built the right kind of tools to see it yet.
So it's not a desert, it's a dense forest.
A dense jungle full of hidden particles and forces. A whole dark sector with particles that don't interact with our light. Axions, dark photons, heavy neutrinos, leptoquarks. We haven't seen them either because they're too heavy for the LHC, which the FCC would solve, or because they interact incredibly weakly, which experiments like LZ and the neutrino projects are designed to find.
And by studying these things, the Higgs, the neutrinos, we're fundamentally studying our own origins.
Precisely. When we collide particles at 100 TeV, we are recreating the energy conditions that existed a trillionth of a second after the Big Bang. We're trying to understand the phase transitions of the universe. Why did the vacuum of space freeze in such a way that it allows for stable atoms and ultimately for life? It's the ultimate archaeological dig.
So where does that leave us? It feels like we're at such a strange, pivotal moment. The Standard Model is the greatest theory ever, and yet we know for a fact that it's wrong. We have these tantalizing anomalies in the data that could be the first light from a new world, or they could just be statistical noise and calculation errors.
It is a strange moment.
And we're standing on the precipice of deciding whether or not to build machines the size of small countries to go and find the answer.
It means we're still explorers. For all our knowledge, we haven't mapped the whole world yet. We've just mapped the beach very, very well. And we're standing at the edge of the sand, looking inland, and realizing there's a vast, dark jungle ahead of us. We can stay on the beach, be happy with our perfect map of the sand, or we can build a bigger, sharper machete and start hacking our way into the trees.
And somewhere in that jungle are the answers.
Or more likely, somewhere in that jungle is the next better set of questions. And in science, a better question is always more valuable than a final answer.
Before we wrap up, thank you to all our partners, sponsors, and scholars who made this podcast and the research possible. We're truly grateful for your support.
And to our listeners, thank you for being part of this journey with us. If you enjoyed today's episode, be sure to subscribe and follow Stack Studios for more informative content. And support us on Patreon.
Until next time, stay curious, keep learning, and let the search for wisdom guide you forward. Have a great day.